Welcome to ePadasala lecture series in computer science. In this particular module, we are going to discuss about computational complexity. We are going to introduce the polynomial problems and non-polynomial deterministic algorithms, and the learning objective of this particular module is to understand the concept of polynomial algorithms, to understand non-deterministic polynomial algorithms, and the main focus of this particular module is going to discuss about NP hard problems. Fine. Last module we introduced the concept of complexity theory. Probably you can recollect that I was telling you that complexity is associated with the difficulty of solving a given problem. Suppose if you are trying to sort 10 numbers, the complexity is less, but the same problem for sorting 1 billion number is associated with much difficulty and hence more complexity. In other words, the difficulty that is associated with problem solving process is what we are calling as the complexity. Complexity, for our convenience, we are trying to divide that into two categories. One is called the algorithmic complexity, where our primary aim is to find the complexity of the given algorithm. In the earlier module, we discussed about finding the input size and expressing T of n in terms of the input size. And another is problem complexity or computational complexity, where we are trying to find the complexity of the problem itself. In other words, we are trying to find the limits of the algorithm so that we can say how hard the problem is all about. For any given problem, solvability is going to be the important criterion. So, what is solvability? A problem is solvable if there exists a program that always terminate and gives the answer. In other words, if there exists an algorithm that terminates, also gives answers correctly, then the problem is said to be solvable. For example, sorting of an array is a solvable problem, because we have plenty of algorithms that can execute and give the answer in polynomial time. Therefore, sorting is a solvable problem. From the concept of solvability, we can find the concept of tractability. A problem is tractable provided if it is solvable and also in time that is less than or equal to some polynomial time. If that is the case, then we can say that the problem is tractable. If a problem exists where we can't ensure these condition means it is called intractable problem. There are many problems that are intractable in nature. For example, traveling salesperson for a larger instance is an intractable problem. What is the advantage of having these notations? From the concept of tractability, we can find the efficient algorithms. The definition of an efficient algorithm is it should be a tractable problem. The advantage of having an efficient algorithm is that it will take lesser resources to get executed. In other words, the usage of resources are going to be optimal. Therefore, we can call those algorithms as efficient algorithms. So, the key of all the thing is polynomial time. In other words, we are saying that an algorithm is tractable if there exists a algorithm whose complexity is a polynomial. In other words, polynomial time is going to be the keyword. What is the implication of this? The implication is a problem is feasible if its solution cost is represented as a polynomial. For example, we say the complexity of insertion sort is order of n square. N square is a polynomial. We say the complexity of matrix multiplication is order of n cube. N cube is a polynomial. In other words, a polynomial is what you say represents the bound of all these algorithms. Who invented this concept of polynomial time? It was independently invented by Jack Edmonds and Alan Cobham, and they proposed this concept of polynomial time. They used this as a reference to say whether an algorithm is efficient or not. What is the concept behind this? Polynomials are closed under composition. For example, if you have two algorithms A and B having a complexity time S of n and T of n, then we can design one algorithm as a subroutine for another algorithm in order to find an algorithm which can solve this given problem. In other words, you can say that the polynomial is closed under compositions. Similarly, polynomials are closed under addition also. In other words, S plus T is equal to T plus S, and if a problem can be solved in two computers using different polynomial time, then we can say that one polynomial is represented as another form of another polynomial. In other words, the same complexity is represented as a different polynomial in different systems, but they are polynomials and are related. Because of these three considerations, we are calling that polynomial is an effective metric. So, in short, we can say polynomials are closed under composition, polynomials are closed under addition, and all sequential digital computers are related. So, because of all these criteria, we say that polynomial time is effective. From this, we can derive the concept of class P or P class problems. What is P? P is a class of decision problems that are solvable in a polynomial time that is in order of p of n, where p of n is going to be a polynomial expressed in terms of size n. So, if there exists a problem that can be solved in a polynomial time, then we can call that as class P. What is the meaning of class? This is for our convenience, where we are trying to group all the problems that are having the similar characteristic as a class. In other words, class P is nothing but a set of problems whose complexity is guaranteed by the polynomial time algorithms. So, class P problems are very efficient. What are the examples of class P problems? Examples are searching. For example, linear search is a polynomial algorithm. Binary search is a polynomial algorithm. For finding the element uniqueness, we have seen some algorithms which are considered as polynomial. Given a graph, can I say that whether two vertices I and j are connected or not is a polynomial problem. In other words, you can say n number of problems which are coming under this particular category. As I said earlier, this concept of polynomial is also related to efficient algorithms. For example, if I have an algorithm like merge sort whose complexity is order of n log n, can I call this algorithm an efficient one? Yes, because the algorithm is bounded by a polynomial n log n. Similarly, order of n square is also a efficient algorithm. What about algorithms like order of 2 power n and order of n factorial? These algorithms are not polynomial, but these are called non-polynomial algorithms. In other words, these algorithms are called exponential algorithms. What is an exponential algorithm? In exponential algorithm, if the input size increases, the complexity of the algorithm increases dramatically. In the first module, we discussed a problem called a traveling salesperson problem, where we have seen that if the number of cities are less, the complexity of the algorithm is also very less. But if the number of cities increases dramatically, the complexity of the algorithm also increases. Hence, these algorithms are not called as polynomial algorithm, but instead as non-polynomial algorithms. Non-polynomial algorithm for large n are intractable. In other words, we cannot solve this problem within the given available resources such as memory and time, and hence characterized as inefficient algorithms. Is this rule standard? Fine. We also face some hurdles in accepting this as sacrosanct. For example, if I have one algorithm whose complexity is n power 100, can we call this algorithm as efficient? Means we face a difficulty, because if n is large, then we have exponential algorithm. So, we are facing a problem in accepting this as sacrosanct. But what is the justification for this strategy? Fortunately, most of the algorithm we encounter in algorithm do not have larger degree. In other words, the degree of most of the polynomials we encounter does not cross more than 3. Therefore, we can come to a conclusion that this strategy is very effective, because order of n power 100 algorithms are so rare, and hence can be conveniently ignored. So, in short, we can say that for most of the algorithms, this kind of classification of efficiency and inefficiency based on the polynomial time is highly relevant. Fine. When we talk about solvability of the problem, is there exists a problem that can't be solved? In other words, are there problems that can't be solved at all? These problems are called unsolvable problems. Unfortunately, the answer is yes. Most of the real world problems are unsolvable in nature. Therefore, the study of computational complexity becomes more important. The essence of this is suppose if the problem given is unsolvable, finding that in the initial stage itself saves lots of energy in terms of time and effort. Instead, if we start the project and later on if we find that the given problem is unsolvable, then it marks the lack of judgment which can cause problems in terms of resources. So, there are lots of problems that are unsolvable. This was indicated by Alan Turing using a problem called halting problems. We encountered Alan Turing in earlier modules. Alan Turing is the father of modern computer science. His contributions are many. Some of the essential contributions of Alan Turing is Turing Machine, which is a computing model which can give you a proof whether a problem is solvable or not, and this was done in association with Church, and this is called Church Turing Thesis, and he has given number of problems, and one important problem is called halting problem, which has got a proof that the problem cannot be solved at all. Some of his other contributions are Turing Test, which explains whether the machine can ever think at all. Fine. First, we will start with halting problem. What is a halting problem? Can we write an algorithm that takes another algorithm as input and check whether the program will halt or not? Halt is nothing but termination. In other words, the algorithm which we are supposed to write should take a problem as input, and it has to say whether the algorithm will terminate or will run infinitely. This is a problem called halting problem. Halting problem is an unsolvable problem. In other words, it is not possible to solve this problem at all. The proof of this problem is given by Alan Turing itself. It is based on the logic of contradictions. So, let us try to see the proof of this particular problem. We take a problem, a program for which we want to test whether this program will halt or not. Then we are giving this as the input for itself. In other words, what is happening is that we write one program and we are giving that as the input for the same problem. If halts program comma program while true, then it loops. So, we say it is print looping, otherwise it is done. So, this is the program. So, what is the implication of this? Suppose if the program takes itself as a input, returns true, that means the program says that this program will halt. However, in this case you can see that if the condition is true, the program keeps on looping. So, that means actually the program is not halting. This is a contradiction. We say the program halt, but actually the program is not halting. On the other hand, if the program returns false, so that means the given program says that the program will not halt, but in the algorithm it halts. In other words, we say that what is happening is nothing but contradictions. In mathematical logic, if you state P is true and in the proof somewhere if not P is also coming as true, then that means it is a contradictions. So, using this use of contradictions that which states that P as well as not P can't be true at the same time, we can say that this is not decidable. Therefore, the conclusion of this is that the halting problem is not solvable at all. The greatest contribution of Turing is halting problem, which one for all proves that there are some problems which can't be solved at all. He extended this logic for Turing test also, and he was aiming to give answer whether the machine can ever think. The Alan Turing test is considered as one of the important litmus tests in artificial intelligence, where you have a judge, you have a program and you have a computer. They are not talking directly, but they are conversing through telephonic or computer network. The computer and the person return the answers in a typewritten form. So, the Turing test is fine if a person and computer masquerade representing the other personality, can the judge consistently determine which set of answers were from a computer and which set come from the machine. Suppose if the judge can't determine, then we can say that the computer is acting very smart, similar to the human person. In other words, the machine is exhibiting intelligence. In other words, this test is called Turing test, and this is considered as a litmus test of whether the machine will ever think or not. Another major contribution of Turing machine is a theoretical machine. So, that means remember those days there were no major computers. So, it was a mathematical model. So, Turing machine is a mathematical model which consists of many basic elements such as a long tape broken into cells. You have a magnetic head that can move one step ahead. So, it will move forward, it will move backward. So, it can also print a symbol. In other words, Turing machine can serve as a mathematical model which can take a program and Turing machine can execute, and if it terminates correctly, we can come to a conclusion that the program will halt or the program is right. In other words, Turing machine can be used as a proofing tool. One of the important contribution of Turing machine is that fine, for all programs this machine can be used. In other words, Church Turing thesis states that Turing machine could theoretically be created that can do anything that a digital computer can do. In other words, the beauty of this mathematical machine is that fine, without having any computers, we can give you a proof that whether a program is right or not. So, the ingredients of this proof is we have to have certain important terminologies. So, we should have something called alphabet. A alphabet is a finite set of symbols. For example, an alphabet can be 0 or 1. So, using this alphabet, a string can be constructed. A string is defined as set of symbols. For example, we can say that 0 0 or 1 0 or 1 1 is a string. An empty string is nothing but a string of 0 length, and when we have lots of strings, we have a set of strings or a language. Language L is nothing but set of strings. For example, if alphabet is going to be 0 1, then all the strings that are derivable from this like 0 0 1 0 1 1 1 1 0 0 0 are all valid strings. We can call this set as a language. A complementary language is a language where if the strings are not present in L, then we can call that as a complementary logic. So, the requirements of using Turing machine is a problem should be taken and it should be converted to a decision problem, where the output is going to be either yes or no. So, the logic is very simple. We are taking decision problems and we are going to check whether this problem can be checked in polynomial time or not. So, take the problem, encode that, take Turing machine and feed the problem as a set of strings to the machine, and if the input string is invalid, then the problem is not right. Turing machine will reject this, and if the input string is valid, but the output is no, then Turing machine will reject this also, and if the string is valid and if the output is yes, that means Turing machine terminates, then we can call that as the accept state. In other words, the problem is solvable. So, using this we can have the hierarchy of problems. So, recollect that we were discussing about polynomial problems P. So, now we can create another set of problems called non-polynomial deterministic algorithms. In other words, these problems are what you say unsolvable problems. So, we create a hierarchy and we are going to define NP hard if you have a problem, if a polynomial type algorithm for a problem would imply a polynomial problem for every problem in NP. In other words, it is very difficult to have a algorithm that can solve all the problems of NP. Many problems are hard to solve. These are some of the problems that are given, like traveling salesperson, n-queen problem, classroom scheduling, packing, as well as scheduling problems. These are some of the problems we have. The other problems that are coming under this hierarchy are co-NP, which is going to be the opposite of NP, and you have NPI intermediate problems like factoring problems and graph isomorphism. The whole thing revolves around the question whether P is equal to NP. In other words, can we make the equivalence of this? In summary, we can say that solvability deals with the question of whether a problem is solvable or not. Tractability checks whether the problem is bounded by any polynomial. Based on this, we can find the concept of P and NP problems, and there are certain unsolvable problems like halting problems, which are considered as hard problems. This is one of the most difficult uh, theorems to prove. So, in fact, it is called a $1 million problem. So, next module we will discuss about how to solve these problems. Thank you very much.